So this video is part 2 on a series of 4 videos on diploma prep for electrochemistry. So part 1 already went through the introductory terms required for electrochem, things like oxidation, reduction, oxidizing agents, reducing agents, half reactions. This video is going to focus largely on outcome 5, 7, and 8. So building redox tables is something you'll always see on tests and diplomas. We'll spend a fair bit of time on balancing full and half reactions and end with just one redox titration example. So building reduction tables is next, or first. So this is one old diploma question that I pulled, pretty typical of what you might see. So we have some data or observations. Hopefully you collected data like this in a lab at some point in your course. And the question is, we have to list the oxidizing agents from strongest to weakest. So to list those, we have to build a reduction table from this data. We don't have to build a perfect reduction table. You could leave out the electrons. You just need the ordering. So the end of the previous video talked about some trends, and they're really important for building reduction tables. So flipping back to the end of the previous video, trends in our reduction table, we've got the OAs on the left, we've got the RAs on the right. We always see things with H+ or acidic half reactions on the OA side. We always see hydroxide on the RA side, and more important, metals are always on the RA side, so elemental metals. Metal ions are mostly on the OA side. There are some exceptions, but this one is a nice starting point. We're going to use that in this example. We have 3 metal elemental metals. So there's no exceptions. These we're thinking RAs. And you can do a quick double check. We see this neutral becoming plus. So that is, in fact, losing electrons oxidized. So this is an RA. But just being able to start on the right track and really quickly do some assigning is key. So if these are all OAs, then the other side is all of our reducing agents. Okay? That's the first thing you have to do in order to sort these. So now we can start going through them and ordering them. So the first bit of data, we do have a spontaneous reaction. So the oxidizing agent is going to be above the reducing agent. So cobalt 2+ is going to have to be on the left-hand side, and we're going to go to the right and down to get our elemental metal. Okay. So a spontaneous reaction has the OA above and the RA down below. Next bit of information, we have no evidence of reaction, so this is not spontaneous. So the RA, the blue, must be below the OA. So this Y3+ must be on the OA side, and it's got to be below it. So we can kind of add that to our bit of data. So we have our OA, and we need to go up. So we've kind of got 3 of them sorted. We can turn this into a reduction table shortly. Let's just keep analyzing the last bit of information or observation. So we have no evidence of reaction again. So we must have the red OA below and the blue RA above. Now we don't have the elemental Y, but I could place that in. It's going to be right across from Y3+. So that's our elemental. And we have to have SM2+ below it on the OA side so that we can go up to it. So we've built, sort of ordered our chemicals, and I'm just going to complete a quick reduction table from this. So the highest up, we've got cobalt, and then we've got the Nd ion across from it. So I'm going to get in cobalt. I'm going to do the OAs first. We've got cobalt, Nd. We got to figure out what charge that is. We can kind of either look to our examples or the answer key. You could always go to your periodic table, but you don't need to bother going to your table when you've got the information in the question. Then we've got Y3+. And finally, SM2+. Now, a proper reduction table would go plus some amount of electrons, and there's just no point filling this in because we don't need it in order to just do our ordering. So we've got our elemental cobalt. I'm not going to bother putting in the solid, but all of these are neutral. And last, we've got... Okay. So now we're ready to answer our question. We just got to reread, make sure we don't flip the order. We want oxidizing agents, so that is this side. And we want them from strongest, which would be at the top, to weakest, which would be at the bottom. So cobalt is number 5. That's our best, or the 2+ ion. Next, we've got number 6. Next, we got our Y3+, that's 8. And last, we have our SM2+, 7. Okay. So this would be a higher mental activity question. Always get one of these on a diploma. You're going to get at least one of these on a unit test as well. So that's our first question, building the table. Sort of a follow-up, also probably a H higher mental activity type of question, would be which of the following represents a non-spontaneous reaction? So we've got to go and use that reduction table. Again, the fact we were incomplete and left out the electrons won't matter. We just need the ordering. So let's look at the first one. So we have Y3+, which is there, reaction with SM, which is there. So this one would be spontaneous. The OA is above the RA. So that is not the correct answer. It is spontaneous. So the X it means not the right answer. Next, we've got Nd2+, and with Y, and Y is also below, the RA is below the OA, so that's not the correct answer. Nd2+ with cobalt. Cobalt is above it. We're going up to the RA, so that would not happen spontaneously. You'd need that's the start of an electrolytic cell, or potentially, so that is our correct answer. And if you've got time, you could quickly double check cobalt 2+. Oh, that's the best OA. That's going to be spontaneous, if anything, and that's, very spontaneous. So C would be the correct answer. So these two are pretty good examples of what you might see on a diploma exam or test. We'll just do a little bit more practice on this skill. This is more of an older question. They tend to not give this amount of data anymore because these can be really easy and really quick to solve if you understand the nature of the best OA and the best RA. So I'm just going to quickly get out OA, RA. So I'm setting up a reduction table. I'm just not going to label it. When you get a whole table of values, the best oxidizing agent, the one that will come first, is the OA that reacts with everything but itself. You just have to sort out what are your OAs and what are your RAs. So again, we're going to use some of our trends. We've got a whole bunch of neutral metals. So these are always reducing agents. Okay. So these must be our OAs in this case. Again, you can always double check. OAs should gain some electrons to become the RA. So you can use the charges. These are neutral to quickly double check, but elemental metals, reducing agents. So what is our best oxidizing agent? What reacts with everything but itself? Well, it's the bottom one. Reacts with 3 check marks, just doesn't react with itself. So that's our number 1. Again, I'm not going to bother with the electrons in our table. Next best, what reacts with 2 things? That would be at the top. That's our second best oxidizing agent. The next will be what just reacts with 1 thing. And then worst would be what reacts with nothing. And then the reducing agents are just going to be the equivalent neutrals. Again, I'm not, just for the sake of speed, I'm not bothering putting in the states. The only thing I and you would need to be careful with is we have this IR and IN. So if you write too quickly and sloppy or answer too fast, you could easily flip those around. So we need to list these from weakest to strongest, and we want the RAs. So we're on the reducing agent side. So we're over here. The weakest would be at the top. So we're actually starting at the top and going down to the strongest. So we've got our weakest reducing agent, and we've got our strongest reducing agent at the bottom. So you have to start with IR. There it is. It looks like that's going to be our answer. And then PD, IN, ZR, only A works. So these bottom two were oxidizing agents. So those could have been kind of eliminated quickly and would just be considering these two. And it looks like they're just the flip of each other. So hopefully those examples will help you with your building reduction table skills, again, be it a test or diploma. So this is definitely on your guaranteed diploma question list. So there's only about 18 electrochem questions. This is one. Next outcome I'll address more in the in subsequent videos, but just talking a little bit quickly about spontaneity in terms of E0 cell. So before you get into the math in this course, you have something is going to be spontaneous if the OA is above the reducing agent. A reaction is going to happen all by itself. We're not going to get a spontaneous reaction if the OA is down below, and we have to go up to the RA in a reduction table. So in terms of E0 cells, we're going to have an E0 that is positive here. So this is going to happen all by itself. Positive voltage, so you buy a battery, it reacts all by itself. It outputs energy. If you have a non-spontaneous reaction, the OA is below, the RA is above, you just have a negative cell potential. It can happen, but you have to do some work. This is like falling downhill. This is like going uphill. Things don't go uphill all by themselves. Non-spontaneous reactions, the electrons don't move all by themselves, but you can force the reactions to occur. Now, you hopefully have calculated percent error in a lab. There's a few variations of this. You're going to get a similar answer no matter how your teacher presents it, but you're going to be comparing your experimental. So you're going to have your voltage or E0 cell that you measure in the lab. There's a lot of different words you could put for that, and you're going to compare that to the voltage or E0 cell that you would predict. So this will give you the difference of how far you're off, and then to turn it into percentage, we're going to divide it by what you'd predict from your table. And then you're just going to multiply that by 100. Some variations, you'll have absolute values. I like to not put the absolute values in, and the way I've written it is if you get a positive error, that just means your answer is high. And if you get a negative percent error, it means it's low. And I think this is an important distinction that I like my students to have the positive or negative, and then your thought of potential errors are different depending whether you're high or low, particularly if you're doing something like thermodynamics. The high and low really matter. Here you're more likely to have a low error. If you don't put your cell together right, your salt bridge is a little small, you tend to get a lower voltage than expected. So now we're on to a pretty intense section, balancing with oxidation states and balancing half reactions. So we're going to balance the equation in this question, and then we'll deal with the actual color, and we'll come back and use this balanced chemical equation in our redox example. So I'm using this as a balancing practice and then later a redox practice. So we're on to the balancing acidic and neutral solutions. Your teacher might have done basic, or your textbook might have had them, but you don't have to worry about balancing basic half reactions. You need to be able to do halves or fulls with oxidation numbers. So we're going to deal with the balancing full reactions with oxidation numbers first. So we've got a unbalanced redox reaction. You can't just use your grade 10 skills to start balancing this. If you use your grade 10 balancing skills, you're not balancing electrons, and you may not be correct if you're balancing. There are some reactions you balanced in grade 10 that weren't actually correct because you weren't taught to deal with electrons. Now that you can deal with electrons, we're going to have to deal with oxidation states and balance that electron exchange first, and then we'll balance everything else. So I'm just going to quickly put in the oxidation states. I'll do the ones that you would have to know from a memorize perspective. So oxygen in a compound is always 2- unless it's a peroxide. There's another oxygen in a compound, another oxygen. Lots of oxygens, S, Mn, we're going to have to figure out. Hydrogen is always +1. And this is a monatomic ion, so its oxidation state is just its charge. There's another ion, it's just its charge, just what you'd expect for hydrogen. And then you'd have to figure out the S and Mn. So I'm not going to spend the time to do that. This sulfur ends up coming out as +4 to balance the -4 of the two O's. Mn, you've got to watch, there's a negative charge here. So the 4 O's is -8. And you need +7 to end up with them to get the minus charge. And the sulfur, you must be +6. And then you're going to have -8 with the 4 O's, and that will leave you the charge of -2. So now we can balance the electron exchange. Let's see, sulfur does change. Sulfur is going from +4 to +6, so that's a difference of 2 electrons. Now, if you do care what agent it is, then you would want to know whether it's a gain or loss. So if we go from 4 to 6, we're becoming more positive. So we actually have to lose electrons. So that's oxidation. So we've actually found our reducing agent. But if you're just balancing, you don't care about the sign. You just need the count. So there's 2 electrons being exchanged for every sulfur. Now we've got to find something else that is changing. So the O is -2 to -2. So oxygen, it's not oxygen, not this oxygen. So it must be Mn, manganese, and it is. So it's +7 going to +2. So that is 5 electrons. Okay. And it's becoming less positive, so it is gaining electrons. Reduced, so that's our OA, but we don't care about that part for our balancing. We just need to know that there's 5 electrons per Mn. Now, we have to balance the whole species, so I always write a second statement for the whole species that's reacting. I kind of use this species as a vague term. It could be a compound, it could be an ion. So we have 1 sulfur in SO2, so that's still going to be 2 electrons for the 1 sulfur. We have 1 Mn. This Mn is going to transfer 5 electrons. Oxygen is going to transfer none, so 5 electrons. And now we're pretty much ready to balance. We have to find the lowest common multiple to balance our electrons. So the lowest common multiple, the electron exchange between 2 and 5, is going to have to be 10 electrons. We're not going to see this 10 electrons in the balanced equation, but some diploma questions will ask you for that count to see if you know how to do this. So we have to times this by 5. 2 times 5 would give us our 10 electrons. And this one, we have to double the 5 to get our 10 electrons. And we've taken care of the electron exchange. And then we're going to be pretty quick to finish balancing. We're going to do atoms other than O and H. We'll balance O with water and H with H+. Now the water and the H+ are already in our equation, so we're not going to have to add them in, just the correct count. So we have 5 sulfurs, so we need to have 5 sulfur on the product side, so 5 times the 1s. 2 Mn, so we need 2 Mn. Now we balance O with water, and again, we've already got it there. I'm not going to count this O. I'll count without it and then see how many waters we need in total. So let's see, we've got a fair bit of oxygen. So I like to use a little bit of a visual aid when there's a fair bit. Oxygen at the reactant side, oxygen on the product side. So we've got 5 times 2, 10 there, plus 2 times 4, 8. So we have 10 plus 8. You can always just add them in your head. We have a total of 18, I'm not counting this water yet. On the product side, 5 times 4 is 20. And then there's no more. So we're short 2. We need to add 2 more to get 20 on both sides. So we're going to need 2 waters. Last, we need to do our hydrogen. The only hydrogen on the reactant side is in the water. So we've got 2 times 2, 4 H's on the beginning. No hydrogen, no hydrogen. All the hydrogen is going to show up here. So we have 4 at the beginning, so we need 4 at the end. So that balances this redox reaction with oxidation states. Most common mistake is not putting in the oxidation states and balancing the electrons correct. Most students who get these oxidation states in will work their way to the correct solution. Now, this wasn't the actual question. We'll use this again. But this question, you always get ones where you have to connect to observations. Starting about 5 or 6 years ago, a bit before COVID, connecting to labs became a lot more important on diplomas. So in this titration, we balanced. We've got the skeleton up above. We're talking about observations. So would it become more acidic, volume change, conductivity, or color? So on page, I'm pretty sure it's 11, you've got a whole bunch of colors, and you pretty much always need to use that table to figure out the color of certain ions. So in D, we've got purple, and that's where you'd realize that permanganate is a purple color. So let's see, A is an increase in acidity. So that means a product would have to be H+. And that is what we have. So we are making H+, we're becoming more acidic. So that looks like a correct observation. Decrease in volume. We've got an aqueous chemicals and solvent on the reactant side. We've got aqueous products, but we're not losing water. We're not creating a bunch of gas and losing anything. I don't love this B distractor, but that's not correct. We're not having a change in volume. You've done redox titrations and you don't see like half your volume disappear mid-titration. Decrease in electrical conductivity. So we're looking for ions, positive and negative ions. The reactants have only one ion, and if we use our balance, there's 1 unit or 1 mole of permanganate. On the product side, we actually have a lot more ions. So electrical conductivity would actually be increasing. And this is a decrease, so that's definitely not correct. Last, we have an increase in purple. Well, we got permanganate. That is going to be purple, but it's a reactant. That purple would be fading. So first looked like this could have been an answer, but it's the wrong trend. So the only correct answer is A. So we're going to keep going with that balancing full and half trend. So we'll balance with oxidation numbers, and I'm going to balance this example actually 2 different ways. I'll balance it with oxidation states, and then you could also balance it with 2 half reactions. Now this one happens to be a disproportionation where this NO2 is going to act as our OA and our RA, but it doesn't change how you carry out the steps. The only thing it's going to tweak is once you notice you have something that is disproportionation, and let's get in those oxidation states and then build from there. And to see its disproportionation, we've got oxygen, that's -2. This N has to balance those 2 O's, so that would be +4. We've got water, +1, -2. We've got nitric acid, so +1, -2, and then you have to figure out the nitrogen. So we got -6 for the 3 O's, +1. So we need another +5 to get to +6 in total to balance the oxygen, and then -2 and +2. And the water is not changing oxidation states for the H or the O. This nitrogen is going up to +5 and down to +2. Now, you don't have to do this, but I suggest when you notice you have something that's disproportionation, you write that chemical a second time. One of them, you're going to connect to one of the products that's going up, and the other one you can connect to the oxidation state that's going down. So this nitrogen that I wrote again, I'm going to connect here. So this was +4 going to +5. So that is a 1 electron transfer per N. There's only one N in NO2. So this NO2 will transfer 1 electron. If we look at our second NO2, to the second time we have nitrogen on the product side, that's a +4 to +2. So this one is a 2 electron transfer per nitrogen, or 2 electrons for that NO2. Now, we don't care which one is oxidation, which one's reduction for balancing, so I'm not even going to bother adding that in. So 1 electron exchange, 2 electron exchange, still have to find the lowest common multiple. This is of electrons between 1 and 2 will be 2. So this is going to be a 2 electron exchange. So we have to double the first NO2. So that literally requires putting a 2 in front. This will now have transfer 2. This will have the other transfer, and the electron exchange will now be balanced. Labeling this 2 ways also helps you balance the N. You can kind of follow these 2 N's are going to end up here. So electron exchange is balanced. Then we're going to do other than O and H. So that's nitrogen. There's 3 in total, but these 2 are going to end up here. This 1 N is going to end up there. So we've got 1, 2, and a third at the beginning, 2, and a third, 3 at the end. So our nitrogen is balanced. Balance oxygen with water. So we have 2 times 2, 4 O's here, plus 2 more, 6. I'm not going to factor in this water yet. So reactant side, product side, there are 6, not counting the water at the beginning. At the end, we've got 2 times 3, 6, plus 1 more is 7. So we are short 1 water, 1 oxygen on the reactant side. So we just need one of these. So you obviously don't have to put the number in, but I'm putting it in for emphasis. And if you have to key in a correct number, you can't leave it blank. You'll be marked wrong. You must key in A1. Last, we're going to balance the H with H+. So no hydrogen, no hydrogen. We have 2 H's there. And we have 2 H's here. So no H+ is needed to be added. So this is not a acidic redox reaction. This would be one of the neutral ones. You don't see a lot of neutral redox reactions, but that is this one. So, fact, it was a disproportionation, had one little twist, but overall not way worse. Now, a lot of teachers will teach this by having students doing 2 half reactions. And this will be my switch or lead into balancing half reactions. We can just net the 2 up and we should get the same redox reaction. So we have the top green and the bottom green pieces to balance. So I've pre-written out the NO2. And I've got to grab, so in one of the reactions, the NO2 is going to become HNO3. So this is one of our halves. The other half is going to become NO. Okay. And we're going to balance these 2. So the sequence for balancing half reactions, I've typed out to be all the steps above the black line. The bottom will be netting the two together. The big difference is you deal with electrons at the end of the step instead of the start when you're using oxidation states and doing fulls. So again, this is just the steps for half. Same sort of key middle steps. So we're going to balance atoms other than O and H. So we've got one N, we've got one N, so that's good. We balance O with oxygen with water. So we've got two N's, we've got two O's, we've got three O's, so we're short of water on this side. So we're going to have to add in a H2O. Then we balance H with H+. So we have two H's in the water compared to just one on the product side. So we need another H, and this is unique balancing. You never did this before this unit, but we're going to add H+ to balance this. Last, we have to do the electron exchange. We have to balance the charges with electrons. So if we think of our charges, reactant side, product side, we're going to add electrons to the high side. So we've got no charge. This is neutral. Water is neutral, so there's no charge on the reactant side. The product side, we have something neutral, and then we have a +1. So the high side is the products, and we've got to bring that down to 0. And we're going to do that by adding 1 electron. So we've balanced this half reaction. We got to run through those steps again with our second NO2, and then we can net the two up. So we're back to the top again, balance other than O and H. Well, we've got one N on both sides, that's good. Balance O by adding water. So we've got two O's on the product side, two O's on the reactant side, one on the product side. So we need another O, and we're going to get that by producing some water. Like, where does it come from? It's coming, we're making more solvent. I guess, where does it go? Hydrogen, we've got no hydrogen at the beginning. We've got 2 hydrogen in our water, so we need to add 2 H+. We're going to be using up some acid that must be there. Last, we're going to balance the electrons. We're going to balance the charge. We have to count reactants, products. We've got neutral and 1+. Oh, sorry, going too quick. I put in H+, but there is 2 H's. So that is a 2+ charge. Neutral 2+, neutral, neutral, no charges on the product side. So in order to balance this half reaction, we've got to get the high side, which is now the reactant side. Sometimes students think electrons always go on one side, but they don't. It's just the high side. You have to bring it down. So we're going to need, down to 0. So we're going to have to add 2 electrons. Now, I don't have room. Typically, I'd write it here. Don't have a lot of room. I'll put it first. The order doesn't matter. This is 2 electrons and NO2 and H+. The ordering has no meaning when we write equations. So that lets us practice half reactions, and then we just need to net these up, and we should have exactly what we had before. Either method will work for balancing full reactions, the 2 halves or the oxidation states. But we can't balance until we balance the electrons. So we've got 2 and we've got 1. So we have to double everything in this top half reaction. So no number here, 1, we'll double it to 2. No number here, which is a 1, we'll double it to 2. No number, we'll double the 1 to a 2, double the 1 to the 2, and double the 1 to a 2. And now we can balance. Our electrons are going to cancel out. And let's see, what else do we have? Oh, the acid cancels out. That's good because we know H+ when we balance it up above. We have water on both sides, but we have 2 at the beginning and only 1 at the end. So we can cancel 1 water out of both sides. We're subtracting when we cancel. So subtract 1 water, and I'm going to subtract 1 water, and that leaves me with 1. So that's going to leave us with 2 and 1 more, 3 NO2s plus our water. It's going to produce 2 HNO3 and our nitrogen monoxide. And we got to the exact same place. So obviously don't do it two ways, but both of these work. I like the oxidation state method. That's what I teach my students to balance full reactions. But I know lots of teachers and colleagues, they just pound home the half reaction, and you can kind of use this for almost anything. Balancing fulls. A couple more balancing halves, just the halves, and then we'll move on to our last section. We have a titration analysis to do. So straight up balancing halves, I've got the steps. Out, balance atoms other than O and H. So that's just the Mn. Now you may want to pause this video, try to balance this yourself, and then hit unpause and see if you did it correctly. So just pausing for a chance to see if you wanted to pause and come back. So the answer is going to be other than O and H, 1 Mn, 1 Mn. We don't care that the state of it has changed from a monatomic ion in a compound. We got 1 manganese. Oxygen, we've got 2 O's at the beginning, so we have to add 2 waters. And most teachers are going to add it at the end. I don't have room. 2 times 2, 4 H's. And we have no H on the product side, so we need 4 H plus. And last, we're going to balance the electrons by balancing the charge. So we have neutral water and then 2 plus for the manganese. We've got something that's neutral, and then we've got 4 plus. So we have to bring the high side down to the low side. So 4 is higher than plus 2. So we need to bring this down to have plus 2 on both sides. Again, some students think that you have to have 0 or neutral on both sides. That is not correct at all. They just have to have the same charge. So we need 2 electrons. We brought down the product side, so that is where the electrons must go. So that's our correct balanced half reaction. You could be asked whether this is reduction or oxidation. I use Leo and Gur to help remember it. So Gur, gaining electrons reduced. Oh, they're not being gained, they're being lost. So this half reaction is a oxidation. Last one of these two. So back running through these steps. Again, you may want to pause the video, solve it, and then hit unpause and see if you got the right solution. So balance other than O and H. Well, there's nothing other than O and H, so nothing to do there. Check that off. Balance oxygen with water. Let's see, we've got 2 O's, we've got 2 O's. Pretty rare, but there is nothing to do there. Sometimes when there's nothing to do, it confuses students. Midway down to the hydrogen, we've got 2 on the product side, so we need 2 on the reactant side. And that's going to come from acid that must be present. Last, we'll balance the electrons. Charge reactant product. We've got a 2 times 1 plus 0. So total charge is plus 2. And just neutral peroxide. So here the high side is the reactant side. We've got to bring that down to the low side, which is 0. So we need 2 electrons to bring that down. So I've got to fit in 2 electrons somewhere. Again, your answer doesn't have to have this sequence. You just need to have 2 H pluses, 2 electrons, and 1 oxygen molecule, and you are correct. I'm grabbing an old diploma question that is relating to balancing. So we have an incomplete. Okay, so that incomplete tells us that things like H plus and water are not put in, and it's unbalanced. That's really key to notice that in any diploma question, be it thermo, where it's normal balancing, or electrochem. And this is a half, and that's super crucial. Students sometimes apply the wrong strategy, whether it's a half reaction strategy or full. So we're applying these steps. So let's jump to the question. Which of the following rows identifies the lowest whole number coefficients for water and H+? So we're going to have to balance this whole thing out. So we got to run through these steps. So we'd balance atoms other than O and H. So we've got 2 Br, but only 1 bromine on the product side. So we can fix the bromine by doubling our ion. Then we balance oxygen with more water. So we have 2 times 3. We have 6 O's on the product side, so we're going to need 6 water. We're going to need that for our answer. Then we're going to balance H. We've got 12 H's here on the reactant side, so we're going to need 12 H+. Now we could keep going, and I'm going to balance the charge, but we don't need it because the charge, the electron count, isn't required here. But let's see, we've got neutral and we've got neutral. So we've got no charge on the reactant side. Product, we've got 2 minuses and then plus 12. So let's get that out. We've got 2 minus. We're going to have to add to that the 12 plus. So that is a total of 10 plus. So we'd have to bring this down to 0. So what's our answer? Water count is 6 and the hydrogen count is 12. So the answer is D. Reasonably common format, and they could have made electrons a potential column. So you need to be able to do that. So we worked through 2 of the more challenging outcomes within general outcome 1, the redox reduction table balancing and balancing halves and complex half, complex fulls with oxidation numbers and the half reactions. Last, we'll just do a redox titration example, and that'll be done the first half. I'm just going to cover up some of my solution and we'll work through it. With titrations, be it acid, base, and Chem 20 or redox titrations, really encourage you to make a little visual aid of what's going on. You need to know the concentration and volume of the 2 reactants that are limiting this reaction. So let's grab that information. So we've got sulfur dioxide gas, causes rain, acid rain, so nothing important yet. The concentration can be determined when titrating. So this is when we're going into titration mode. Standard potassium permanganate. We've got unbalanced reaction. Okay, so as soon as we see this is unbalanced, we need to use the balanced version. And we did this exact example already in one of the first questions. So I'm not going to rebalance this. I'm just going to pull our balanced equation from one of our first slides. There it is. So it was this slide. So we have 5, 2, 2, 5, 2, 4. So this would be using oxidation states to balance this was the strategy I like to use, not 2 halves. So we're going to grab our key information and organize it. A common mistake is mixing the volumes with the appropriate chemical. So we have 150 milliliters of SO2 requires 31.5 mils of 0.1 permanganate. So all of these numbers are referring to permanganate. So that's our MnO4. So our concentration is 0.10. 0.01. 0.5 milliliters. Now there was 150 mils of SO2. Now on your diploma, you can write all over that exam. So I would bring in different colors and color code titration questions like this. And color coding is useful in a lot of questions. 150 mils, and we're asked what is the concentration of SO2. Okay. Water is going to be an excess reagent, so we need to figure out how many moles we have of permanganate. You always want to start with the chemical you know, the C and the V, and then we're going to turn this chemical into that chemical, which is the second step, and then the third step will be getting the concentration of this chemical. So that's what I've kind of laid out. So get moles of permanganate, get moles of sulfur dioxide, and then we'll get concentration of sulfur dioxide. We have things nice and organized. So this is all blue data. To get moles, you need concentration times volume for solutions. I grab my concentration. Now the volume, you've got to convert your units. You divide by 1,000 to get liters. So we have our moles of permanganate. Next, we've got to do step 2, get moles of turn moles of permanganate into moles of sulfur dioxide. And that's where this 2:5 ratio will come in. So I pull down our permanganate moles, and then we're going to turn permanganate into sulfur dioxide. This is our stoichiometry, and there are 5 sulfur dioxides required for every 2 permanganates. So then we can run this math and we'll convert to SO2. And I got 0.0007875. Now you're going to leave all the digits in your calculator. Do not round. I'm not going to write everything that's in my calculator. Now I like to write the chemical after the moles, so I don't get confused of is this permanganate moles or is this MnO4 moles. Really encourage you to do that. I even like to put them right in my math. So this is moles of MnO4, and MnO4 chemical here cancels there, and this is the chemical that is going to be the moles at the end of this step. So we're halfway through. We just need to get the concentration of sulfur dioxide. Now we know the moles, and the question gives us our volume, so we're just putting them together, and we're just about done with this titration. So our moles, pull that down. Again, you're using all the digits on your calculator. Do not round. Divide by the volume. We need it in liters. So it's dividing by 1,000 to go from the 150 mils down to our liters. So I got a concentration in moles per liter. And this is where you would want to round your answer to the proper significant figures. Now, you really don't have to worry about this, sadly, on diplomas, because the question will just basically tell you how many. So you could leave them all, but you should know how to round, leaving Chem 30 going into post-secondary. Now, this question has an extra M in it, so that is millimoles. Milli is counting by 1,000. So to get this into millimoles, to see which answer is right, you probably know which one it is already. This is a multiply by 1,000 to get to the milli. So we're going to move our decimal place. Don't even need a calculator for this. 1, 2, 3. So 5.25 millimoles. So that is our C is our correct answer for the concentration. In Chemistry 30, you should be able to handle millimole, milli anything, kilo anything, and mega will show up sometimes, most likely in the thermodynamics unit. Prefixes like nano, pico I don't think I've ever seen those on a diploma. So that wraps up general outcome number 1. Hopefully that helped you, and stay tuned over the next coming days or weeks. Redox. The following video number 3 will come out, which is into electrochemical cells, sort of the intro outcomes. And then video 4 will be the cell potential part of electrochemical cells.